Welcome dear audience, students and scholars. Here I'm Dr. Amjad Ali. In this video we will learn about the Solow Growth Model. Dear scholars, one of the prominent economists, James Strobel, once said that the question of growth is nothing new but a new disguise for an age-old issue, one which has always intrigued and preoccupied economic, the present versus the future. If you have ever spoken with your grandparents about what their lives were like when they were young, most likely you learned an important lesson about economic growth. Material standard of living have improved substantially over time for most families in most countries. This advance comes from rising income, which have allowed people to consume greater quantities of goods and services. To measure economic growth, economists use data on gross domestic product, which measure the total income of everyone in the economy. The real GDP of the United States today is more than 5 times its 1950s level, and the real GDP per person per capita is more than 3 times its 1950s level. In any given year, we also observe large differences in the standard of living among countries. So we have identified in our classical model the factor of production, labor and capital, and the production technology as the sources of the economy's output, and as far as total income. Differences in income then must come from differences in capital, labor and technology. Our primary task in this video is to develop a theory of economic growth called the Solow Growth Model. In our classical model, we have described how economy produces and uses its output at one point in time. The analysis was static, a snapshot of the economy. To explain why our national income grows and why some economies grow faster than others, we must broaden our analysis so that it describes changes in the economy over time. By developing such a model, we make our analysis dynamic, more like a movie than a photograph. The Solow growth model shows how saving, population growth and technological progress affects the level of an economy's output and its growth over time. The accumulation of capital, the Solow growth model is designed to show how growth in the capital stock, growth in the labor force, and advances in technology interact in an economy, as well as how they affect our nation's total output of goods and services. We will build this model in a series of steps. Our first step is to examine how the supply and demand for goods determine the accumulation of capital. In the first step, we assume that labor force and technology are fixed, and then we try to relax these two assumptions in our coming video or coming session. Okay, the supply and demand for goods. The supply and demand for goods play a central role in the static model of the closed economy. The same is true for the Solow model here. By considering the supply and demand for goods here, following question will be answered. What determines how much output is produced at any given time, and how this output is allocated among alternative uses? The supply of goods and the production function. The supply of goods in the Solow model is based on the production function, which states that output depends on capital stock and labor force. So then our production function y is equal to the function of labor and capital. So we have the Solow model. Assume that the production function has a constant return to scale. This assumption is often considered realistic, and as we will see in our coming session, that it helps us to simplify our analysis. We have the production function as a constant return to scale in our classical model. So we have zy is the function of zk zl. For a positive number z, that is, if both capital and labor are multiplied by z, the amount of output is also multiplied by z. Then the production functions with constant return to scale allow us to analyze all quantities in the economy relative to the size of the labor force. To see that this is true, set z is equal to 1 over L. In the preceding equation we obtain that y over L is equal to function of k over L, and we have 1. This equation, so here we have this equation, shows that the amount of output per worker is a function of capital per worker k over L, and we have here 1 as a constant, and we suppose here we ignore it. Okay, while talking about the supply of goods and the production function, the assumption of constant returns to scale implies that the size of the economy as measured by the number of workers does not affect the relationship between output per worker and capital per worker. Because the size of the economy does not matter, it will prove convenient to denote all quantities in per worker term. So let's designate quantities per worker with lowercase letters. We have here y in lowercase is equal to y over L is per worker output, and we have k lowercase is equal to k over L is per worker capital, or capital per worker. So the production function can be written as y is the function of capital. So here we have defined that output per worker is the function of k and 1. So we have supposed that 1 is a constant, so that's why we ignored it here. Okay, then the slope of this production function shows that how much extra output a worker produces when given an extra unit of capital. This amount is the marginal product of capital, MPK. So mathematically it can be written as MPK is equal to function of k plus 1 minus function of k. So this means that next year capital, or next quantity is capital minus the current quantity capital. So let's see a graphical presentation that how the production function work while when we have a diminishing marginal product of capital. So the production function, we have a capital per worker on x-axis, and we have output per worker on y-axis, and we have a flatter production function, output function, and we have we know that if we want to if we increases that capital per worker, we get that amount of output, that is MPK. So as the amount of capital, we have the production function, as the amount of capital increases, the production function become more flatter. Here see, more flatter, indicating that the production function exhibits a diminishing marginal product of capital. When k is low, the average worker has only a little capital to work with, so an extra unit of capital is very useful and produces a lot of additional output. When k is high, the average worker has a lot of capital already, so an extra unit increases production only slightly. So this figures explains that the production function shows how the amount of capital per worker K determine the amount of output per worker. We have y is equal to function of K. The slope of production function is the marginal product. Here we have the slope of production function, the marginal product of capital. If K increases by one quantity, that amount of quantity, so the output increases by MPK, that amount of quantity. The production function becomes flatter as K increases, indicating a diminishing marginal product of capital. Okay, the demand for goods and the consumption function. Okay, while the demand for goods in the Solow model comes from the consumption and investment. In other words, output per worker Y is divided between consumption per worker C and investment per worker I. So we have per worker output is equal to C plus I. So this equation is the per worker version of national income account identity for an economy. Notice that it omits the government purchases and net exports because we are supposing that we have a closed economy in the Solow growth model. So Solow model assumes that each year people save a fraction S of their income and consume a fraction 1 minus S. This idea can be expressed as following consumption function. We have C is equal to 1 minus SY. So here we have S is the saving rate, is the number between 0 and 1. Keep in mind that various government policy can potentially influence a nation's saving rate. So one of our goal is to find what saving rate is desirable, but here we are supposing that saving are given, or we can say that saving are constant. Okay, while talking about the demand for goods and the consumption function, to see what this function implies for investment, substitute S1 minus SY for C in the national income account identity. So we have Y is equal to 1 minus SY plus I. So rearrange the term to obtain I is equal to SY here. So this equation shows that investment equal saving, as we have also approved in our classical model, that the saving rate S is also a fraction of output devoted to investment. Okay, now introduce the two main ingredients of the Solow model, the production function and the consumption function, which describe the economy at any moment in time. For any capital stock K, the production function Y is equal to function of K determines how much output the economy produces, and the saving rate as determines the allocation of that output between consumption and investment. Okay, growth in the capital stock and the steady state. At any moment, the capital stock is a key determinant of the economy's output, but capital stock can change over time, and those changes can lead to economic growth. In a particular, two forces influence the capital stock: investment and depreciation. While talking about investment, is expenditure on a new plant and equipment, and it causes the capital stock to rise. Okay, while talking about the depreciation is the wearing out of old capital, and it causes the capital stock to fall. Let's consider each of these forces in turn. It has already noted investment per worker I equals SY. Okay, by substituting the production function for y, we can express investment per worker as a function of the capital stock per worker. We have I is equal to s function of k. This equation relates the existing stock of capital K to the accumulation of new capital I. So let's see a graphical presentation that how output, consumption and investment actual work with one another. So we have output, consumption and investment graphically presentation here. So we have a capital per worker on x-axis, and we have output per worker on y-axis, and we have a flatter output function, and we have a saving investment function. So we have consumption per worker, and we have investment per worker, and we have total we can say that output per worker. This part is presenting the output per worker. So output per worker is distributed between two parts. The first we can say that the consumption part, and the remaining will be used for investment. So this figure illustrates that how far any value of k, the amount of output, is determined by the production function fk, and the allocation of that output between consumption and saving is determined by the saving rate s. So the saving rate determines the allocation of output between consumption and investment. For any level of capital, output is Fk, investment is SFK, and the consumption, we have the consumption Fk minus SFK. Okay, let's discuss about the depreciation rate. To incorporate depreciation into the model, it assumes that a certain fraction delta here of the capital stock wears out every year. Here we have delta in the lower case in Greek letter delta, so we can call it delta is the rate of depreciation, as we have discussed the other variable as a per capita rate. So that's why we are presenting the depreciation as a rate of per capita, like that. So for example, if capital loss an average of 25 years, then the depreciation rate is 4% every year. Then we have delta is equal to 0.04. The amount of capital that depreciates each year is delta k, and it can express the impact of investment and depreciation on capital stock with this equation, that change in capital is equal to investment minus depreciation. We have delta k is equal to I minus delta k. So this delta here represents the change in capital between 1 year and the next year, because investment I equals SFK, so we can write this function as delta k is equal to SFK minus delta k. So let's see a graphical representation that how depreciation actually work. So here we have capital per worker on x-axis, and we have depreciation per worker delta k on y-axis, and we have a constant rate of depreciation delta k. So a constant fraction delta of the capital stock wears out every year. Depreciation is therefore proportional to the capital stock. So the higher the rate of we can say the stock of capital, the greater the amount of output and investment, yet the higher the capital stock, the greater also the amount of depreciation in the economy. So let's see how depreciation work in the investment and in our steady state decision of capital stock. So here we have investment, depreciation and steady state situation. So we have capital per worker on x-axis, and we have investment and depreciation on y-axis, and we have a constant rate of depreciation, and we have investment function like that, and we have where the investment and depreciation curve intersect one another. This is our steady state level of capital per worker. We have K static, and that is, at that point we have steady state investment I static and steady state depreciation K static, because at this point depreciation and investment are equal. So what happens to before the K static and what happens to after the K static? So here we have a single capital stock K static at which the amount of capital equal the amount of depreciation. If economy finds itself at this level of capital, the capital will not change because the two forces acting on it, because we have here two forces, investment and depreciation, just balance. At that point we have K static and delta K is equal to 0, so that the capital stock K and amount of output are steady state over time rather than growing or rather than reducing. We therefore call K static a steady state level of capital per worker. So the steady state is significant for two reasons. As we have just seen, an economy at a steady state will stay there. In addition, and just as important, an economy is not at the steady state will go there. So that's regardless of the level of capital with which the economy begins, it ends up with the steady state level of capital. In this sense, the steady state represents the long-term equilibrium of the economy. To see why an economy always ends up at the steady state, suppose that economies start with less than the steady state level of capital, such as we have here K1. Okay, at this point capital stock increases because investment exceeds the depreciation. So see here we have a higher level of investment I1 and we have a lower level of depreciation. So over time the capital stock will increase toward the steady state capital along with the amount of output. So it approaches to the steady state capital K static. Okay, similarly we have to suppose here we have a point that higher level of capital as compared to our steady state level of capital. So here we have a higher level of investment. So here we have capital stock decreases because depreciation exceeds the investment. So see here we have the higher level of depreciation as compared to level of investment. So the capital stock will fall, again approaching to the steady state level. Once the capital reaches the steady state, investment and depreciation equals, and there is no pressure for the capital stock to either increase or decrease. How saving affects growth? Consider what happens to an economy when its saving rate increases or its saving rate how the saving rate affects the economic growth of the economy. The Solow growth model shows that saving rate is a key determinant of the steady state capital. If the saving rate is high, the economy will have a large capital stock and a high level of output in the steady state. If the saving rate is low, the economy will have a small capital stock and a low level of output in the steady state. Okay, this conclusion is a light on many discussion, we can say that related to our fiscal policy, how the fiscal policy work. So let's see a graphical presentation here, that an increase in saving, how the increase in saving affect the economic growth of the economy. So how saving affect the growth? We have an increase in the saving rate. So we have capital per worker on x-axis, and we have investment and depreciation on y-axis, and we know that we have a constant rate of depreciation delta k, and we have saving and investment function s1 fk. So we know that the intersection of these two curves decides the steady state capital. So here we have K1 static. So by rising the amount of saving, so an increase in the saving rate increases or raises the level of investment, and we reach on this point. So this will raise our steady state level of capital. So by increasing saving and investment, we have a higher level of steady state capital. So this figure shows that economy is assumed to begin with a steady state with saving rate S1 and capital K static. When the saving rate increases from S1 to S2, the SFK curve also shifts upward, and the initial saving rate and the initial capital stock, the amount of investment also increases, just offset the amount of depreciation, and immediately after the saving rate rises, investment is higher, but the capital stock and depreciation are unchanged. Therefore, investment exceeds the depreciation, and capital stock will gradually rise until the economy reaches the new equilibrium steady state, and that is K2 static, which has a higher capital stock and a higher level of output than the old steady state, if we have output here. So we have here main question that what does the Solow model say about the relationship between saving and economic growth? Okay, higher saving leads to a faster growth in the Solow model, but only temporarily. An increase in the rate of saving raises growth only until the economy reaches the new steady state. If the economy maintains a high saving rate, it will maintain a large capital stock and a high level of output, but it will not maintain a high rate of growth forever. Policies that alter the steady state growth rate of income per person are said to have a growth effect. We will discuss in the growth effect in our coming session. Okay, by contrast, a higher saving rate is said to have a level effect because only the level of income per person, not its growth rate, is influenced by the saving rate in the steady state. Know that we understand how saving and growth interact, we can more fully explain the impressive economic progress of Germany and Japan after World War II. Not only were their initial capital stock low because of war, but their steady state capital stock were also high because of their high saving rate. Both of these facts explain the rapid growth of Germany and Japan during 1950s and 1960s. So this is all about the solo growth model. When we have a constant supply of labor and technological progress. So see you with another video. Ciao.